In this video, we're going to work on problem number 11 in section 2.7. So we're dealing with demand, revenue, and profit. So we're going to go over this entire problem, parts A and B, but then I'm also going to take a second and talk about some big picture things with these kind of problems. So let me read through this problem and underline some of the important things to consider. So it says, until recently, hamburgers at the city sports arena cost $2 each. So this $2 each is a cost, and that's a price. The food concessionaire sold an average of 10,000 hamburgers, so that 10,000 is the quantity, on a game night. So just to recap, he's charging $2 and he's selling 10,000 hamburgers. Okay, then they go on to say when the price was raised, so you're increasing the price to $2.40, hamburger sales dropped off, so they fell to an average of 8,000 per night. Assuming a linear demand curve, find the price of a hamburger that will maximize the nightly hamburger revenue. So I really have no costs here. I'm just dealing with revenue. Now, I don't really have an equation for revenue yet. So that is going to be your first project. So one of the underlying things that you have to know is that price, and that's little p, equals, because they say it's linear, it's going to be sum A, which is your y-intercept, plus your B, which is your slope, times Q, which is the quantity sold. So B tells me how the quantity changes with a change in price. So B is really change in Y over change in X, but in this case it's change in P over change in Q. So that's some overview. Looking ahead to part B, it says suppose that the concessionaire has fixed costs, that means they do not vary, of $1,000 per night, and then here's your variable cost of 60 cents per hamburger. Find the price of a hamburger that will maximize the nightly hamburger profit. So your costs consist of two things, fixed costs and then variable costs, which are multiplied by, so that's per, each hamburger. So in the first situation, we're going to maximize revenue, and in the second situation, we want to maximize profit, and that's going to be profit with a big P. All right, so that's some background. I'm going to move to the next slide, and we'll start setting up some equations. So you may want to just keep your textbook handy so that you can refer back to the question as we go through it. All right, let's do a little overview here. So far, we know a couple of things. So for part A of our problem, we know that one price would be $2. So the price of $2 gives me a quantity of 10,000 hamburgers. Then we know a second piece. We have to read this carefully. When the price was raised to $2.40, so my new price is $2.40. Notice that they didn't say that the price was raised by $2.40. That would have made my new price $4.40. Do you see the difference? So the price has been raised to $2.40. And now let's look at the other piece of it. When that happened, hamburger sales dropped off to an average of 8,000 per night. So they didn't drop by 8,000 per night. They dropped to 8,000 per night. So in our situation, this is what we have. Price is a function of quantity. And your price curve is your demand curve, and your demand curve is generally downward sloping. They told us it's linear. What do we know? We know 2 points. What are those 2 points? And I want to write them in terms of x, comma, y, because this is probably where we had the errors that we're having to make this problem difficult. So what's your x? Well, your q is your x. What's your y? That would be your p. So we're calling them p and q, but I need you to recognize what they are. Given that situation, now write coordinate pairs. So what do I have? I have 10,000 in the x position and $2 in the y position. Then I have 8,000 in the x position, and I have 240 in the y position. So we need to figure out the price equation. Well, the form that we like so much in calculus, because it's easy to work with, is point-slope form. So let's see. That is y minus y1 equals m times x minus x1. Looking at my chart, let's change this to p's and q's. So remember, our y's are the p's. So this is going to be, our point slope equation will be p minus p1. And really I should probably make this a small p, but know that this p is price and not profit. So just know that. And then I have m, and now I have q minus q1. Okay? So we have 2 points to work with. This is 1 point. This is 2 points. So I can plug in either one here and here. What about the slope? What's your equation for slope? Slope equals change in y over change in x. So in our situation here, slope equals, remember your y's are your p's, change in p over change in q. Alright, so we have a lot of background information here. So let's go over to the next slide and we'll work out the equation. Alright, in this slide I've set up some information on calculating the slope. So here is our points. And remember, your points are x comma y, but your x is your q and your y is your p. Because remember, your price equation or your demand equation looks like that. Okay, so what I did was I calculated the slope. So the slope is just y1 minus y2 over x1 minus x2. So when I do the math, I get negative 0.40 over 2,000. So what I did was I multiplied the top and the bottom by 10. And you're allowed to do that because that really is just a fancy 1. That gives me negative 4 over 20,000 because you want to keep your slope as a fraction. So doing it as a decimal is not going to really help me. So here's my slope, and I reduce. I get negative 1 over 5,000. So far we have our slope. And what are we trying to get? We're trying to get a demand equation. So I know my demand equation is going to be price equals some y-intercept plus slope, which now I know is negative 1 over 5,000 times q. So we are now ready to put this slope that we've just identified into point slope form of the demand equation, and then we're going to change it back to this form. What is this form? This is slope intercept. So next slide, we'll do a little bit more work. Alright, let's work on our equation. And this, again, is the price equation, also called the demand equation. So I have a slope. I know that normally point slope form is going to be the generic y minus y1 equals m times x minus x1. So we know that the slope is negative 1 over 5,000. We know that our x's are the larger values that are in the first part of the coordinate pair. So we get to just pick one point. I'm going to pick the easiest of the two, which is going to be the 10,000 comma 2 point, because those numbers are just easier to work with. You would get the same answer regardless of which point you picked, but I'm going to pick that point. So y minus y1. So very carefully, my y1 is 2 equals negative 1 over 5,000, and then x minus x1, and my x1 is 10,000. Alright, so this is a good form to start off with, but I want to get it into slope-intercept form so that I can get a revenue function, because that's my goal. So move your 2. So I'm going to say y equals 2, that's positive now, minus 1 over 5,000 x, minus times a minus is a plus, plus, so I have plus 10,000 over 5,000. Okay, that's not bad. 10,000 over 5,000 is 2. So that's 2. This is 2. And here's my slope, minus 1 over 5,000 x. Combine like terms, and I have 2 plus 2 will get me 4. So my equation is going to be y, and why did I change that now since we know we're dealing with p's and q's? So the y value is our p, so price equals 2 and 2, 4, 4 minus 1 over 5,000, and our x is our q. Okay, so that was a lot of work, because I did very slowly, but we now have a price equation. And we're going to use this equation as we work further into the problem on the next slide. Alright, so here's our price equation that we just worked through. Here is a graph of what our price equation looks like. So this is our demand equation. So it's a price equals, but it's also called a demand equation. So this is the part you need to make a connection with. We are trying to work through revenue. So what is revenue? Because the problem says, assuming a linear demand curve, find the price of hamburger that will maximize the nightly hamburger revenue. We have yet to mention the word revenue, so this is the time. So revenue is price, so whatever price you charge, times how many you sell. That is R, or revenue. So if I know that my price equals 4 minus 1 over 5,000 Q, then price times quantity will equal 4Q minus 1 over 5,000 Q squared. Price times quantity equals revenue. Okay, that's what we want to maximize. So we're going to take our revenue equation on the next slide and maximize it. Alright, here's our revenue equation. Take the first derivative. R prime equals 4 minus 2 over 5,000 Q. That's your first derivative. We're trying to maximize it, set it equal to 0, and then we're going to solve for the Q that makes this function have a slope of 0, which is either the max or the min. So as we're going through this, we're going to now set R prime equals to 0, so therefore 4 equals 2 over 5,000 Q. So how can I get Q by itself? What if we multiply both sides by 5,000 over 2? So 5,000 over 2 times 4 equals, I had 2 times 5,000, and I said multiply both sides by 5,000 over 2. The Q remains. On the right side, these numbers cancel, thus the coefficient of the Q is now 1, and I can cancel on the diagonal. So 2 times 5,000 is 10,000. 10,000 equals Q, and that is the critical value. All right, now I'm hoping that that works, that 10,000 is the quantity that maximizes the revenue. But I don't really know that's the case until I take the second derivative and figure out whether my function is concave down or concave up. That's going to happen on the next slide. Okay, so I rewrote our expression for R prime, which is the first derivative, which is also marginal revenue. And let's get R prime. And before I continue, I just want to put my negative here. Oops. Let me put my negative here because I wrote that incorrectly when I transcribed it. So now R prime prime equals negative 1 over 2500. No matter what Q I have, because there's no Q in the second derivative, this term is always less than 0. If it's always less than 0, my revenue function was concave down, so therefore it must have looked something like that. And therefore the CV that I found, and that CV was what quantity? Okay, it was 10,000, and that CV yielded a revenue that was a max. So I've answered one question. I know that my Q has to be 10,000 to make sure that I have a maximum revenue. How do I figure out what price I should charge? Well, it just so happens I don't really need to do the work, because when 10,000 was sold, they told me the price was $2. But we can verify that because we have an equation for price. Remember that price equals negative 1 over 5,000 Q plus 4. So if you plug in for Q, so this is negative 1 over 5,000, this is 10,000, plus 4, what am I finding? These can cancel, leaving a negative 2 behind. Negative 2 plus 4 indeed does equal 2, and that is your price. So what we've found, and I'll put it down here, in order to maximize revenue, the price should be at $2, and the quantity sold will be then at 10,000, and it's 10,000 hamburgers. So that's part A. Now we're going to investigate part B. Okay, part B introduces some costs. We had no costs to worry about last time, so therefore we were only trying to maximize our revenue. So part B says, suppose that the concessionaire has fixed costs, so this is costs. Fixed costs don't vary with what he sells. So that's just $1,000 every single night. So maybe that's what he has to pay to rent the facility. That's a cost. He can sell no hamburgers and still pay $1,000. Or he can spend 1 million hamburgers and still pay $1,000 in rental fee or fixed cost. Then you also have a variable cost. That may be, say, the price of hamburgers, the price of the gas for the grill. It could be all kinds of things. It could be the price of hamburger buns. So that's going to vary with what you sell. So that variable cost is an additional cost, and it is 0.60 per hamburger. So our hamburgers are Q's. So the C is cost, the hamburgers once again Q's, and I have a variable cost of 60 cents a hamburger. So now it says, find the price of a hamburger that will maximize the nightly hamburger profit. Profit is a new term for us. We've talked about price, we've talked about revenue, we've talked about cost, now we're talking about profit. So what is profit? So profit equals your total revenue minus your total cost. All right? So if you want to maximize your profit, you need to know total revenue and total cost. And we did find out a revenue equation from the previous part A. That revenue equation still works. So for total revenue, and I'll just call it revenue because that's how we've discussed it. So revenue, as we found in the previous example, you can express it as -1 over 5,000, and we had Q squared plus 4Q. Because remember, our revenue was price times quantity. And remember, we had to get a demand equation for the price. We got the demand equation, we multiplied by Q, and that was our revenue. So price times quantity is always revenue. So here's our revenue. Here's our cost. Profit is revenue minus cost. Let's do that on the next slide. All right, so what have I written? Profit, and I wrote out profit again, equals -1 over 5,000 Q squared plus 4Q. Okay, and I just happened to catch one little thing, so let me fix this. So your cost equation is actually 1,000 plus 0.6. So let me not mess that up. So this is 1,000 plus 0.6. Okay, that's better. So now let's see what we're going to do. We're going to distribute this negative two places, and then we're going to combine like terms. So I'm just going to use P for profit. Profit equals -1 over 5,000 Q squared plus 4Q minus 1,000 minus 0.6Q. So we can combine like terms because I have a Q here and a Q here. So I find that profit equals -1 over 5,000 Q squared. Instead of saying plus 4 and minus 0.6, let's just say plus 3.4Q minus 1,000. Okay, that's my profit equation. In order to maximize profit, I want to know where this equation, and it's a quadratic, where it has a slope of 0. It has a slope of 0 where P prime equals 0. So let's take the first derivative. So we get -2 over 5,000 Q plus 3.4. We're going to set that equal to 0, and we're going to solve that. On the next page, I'll do that. Okay, so I rewrote P prime. So I think I forgot the Q, so let me just look, and certainly I did. So there's a little Q here, of course. Okay, set it equal to 0 and solve. So I have 2 over 5,000 Q equals 3.4. So multiply both sides by 5,000 over 2. That cancels. That becomes a 1. Do the same thing over here. And if you do the math, you'll find that Q is going to equal 8500. Okay, that's our Q. Okay, so at this point, what we want to do is make sure that that Q is really maximizing my profit. So we're going to analyze the second derivative. So look where your first derivative is right there, and we're going to do the second derivative. So P prime prime is going to equal negative 2 over 5,000. And because it's not dependent on Q at all, you can confidently say that this is always going to be less than 0. If it's less than 0, my profit function was concave down, and that means that my profit function looked like this. So when I found something with a slope of 0, and that something was 8,500 for my Q, and this is, remember, profit, then by checking the second derivative, I see that my function, this function, was concave down, and therefore I have a max. So that's great. So I have to go back and look at what they've asked me to find. So looking back at the question, remember, you're always going to be looking back and making sure you're answering the question. So they want to know the price of a hamburger that will maximize the nightly hamburger profit. All right, so we have a problem because all we have found so far is the Q. So if I had stopped here, I have proven that the Q I found maximizes the profit, but that's not actually the question. So we're going to take the Q we found and plug it back into the price equation, also known as the demand equation, to figure out what price I should sell each of these 8,500 hamburgers for. And we'll do that on the next slide. On this slide, I've written down the answer we found in B, and our answer is not complete because it's the quantity and we need the price. So go back to the price equation that we derived in Part A. It's the same scenario, so we can use the same price equation. So now that we have a value for Q that we have proven will maximize profit, let's figure out the price that this hamburger seller should set. So my price equals negative 1 over 5,000 times 8,500, because that's our Q, plus 4. And when you distribute and simplify this, you will get a price of $2.30, and now we are done. So this person's going to sell hamburgers, all 8,500 of them, at a price of $2.30, and we have now answered our question.